let's start. Hello everyone, my name is Boros and I work as a consultant at Boros. And we will talk about sysbench and benchmarking in general, and a bit about benchmarking in general. This talk is beginner level, so you would benefit the most from this if you have never seen sysbench or did very little stuff with it. This is mostly based on my experience that when I help people about benchmarks, that's what was useful for them, and it's kind of condensed into this talk. So we will talk about benchmarking in general. We will talk about benchmarking I/O subsystems with sysbench fileio. We will talk about benchmarking MySQL with sysbench, and I will give you some tips on how did I produce the graphs I used, because last time I did this talk, this was the first question. So what is a benchmark? A benchmark is a synthetic workload. And it doesn't represent a real-life workload, but it is really good for comparison. And you can measure your systems with benchmark, or you can simulate your actual workload. But the actual workload, simulation of the actual workload is a lot less repeatable than the benchmark, but the benchmark is not necessarily close to the real workload of your application. So it's like with everything in IT, you can choose if your testing method will suck this way or that way, right? So, or you can put it better that an engineer's job is to make the right compromises. Sysbench is pretty easy to use. I recommend to always use trunk 0.5 sysbench. This is how you can compile it. Fred creates nice packages for Red and Fedora out of it. I always use his stuff, almost. So, let's do a fileio benchmark. This is how you create a set of files for fileio. We create 32 gigs of files here. The number of files are 32, so each file is 1 gig, and the prepare command will create the files which the tests will be performed on. And the benchmarks which I will discuss were made on my laptop, so they are readily reproducible. All this was benchmarking my laptop's SSD. So there are some parameters which we will use during the benchmark. First is the block size. We will use 16K because that's the InnoDB page size. We will use the total size of files and the number of files. The number of files can be important because some file systems like ext3 and ext4 have certain bottleneck on writing the inode table. So if you do it with only one file, you may hit that. And the database is usually more files as well. We will use direct I/O. We will initialize the random numbers, the pseudo-random numbers at the beginning of the benchmark, so we won't hit a bottleneck on random number generation. We will vary the number of threads. We will test synchronous and asynchronous I/O, and we will test random reads, writes, and random reads, writes in mix. Okay, we will also use the next requests parameter, so we don't limit the benchmark based on requests. The next time parameter, and we will capture the metrics every second. So this is how the output looks like. This is a write test. This field shows you the sample, read throughput, write throughput, fsync rate, the response time for the given operation, and the response time is 95th percentile response time. And when I said that we vary the number of threads, does this actually matter, right? We are benchmarking the laptop SSD. A laptop SSD can do 1,000 IOPS or 2,000 or whatever. It's a parameter of the SSD. Do we have to bother with threads? Yes, probably. The correct answer for this is it depends, which happens to be the correct answer for 95% of database-related questions. So, in case of synchronous I/O, our first test, we will wait until the I/O request completes, and only then have the result. In case of asynchronous I/O, we don't wait until the completion of the I/O request, but rather check back later and see how it goes. So in case of asynchronous I/O, adding more threads or removing them doesn't matter that much because we are not doing busy waits. In case of synchronous, synchronous I/O, the number of threads we will use matter a lot. You will see it from benchmark results. And I like to show stuff live, so I wrote a little script which just does the fileio. What? Yes. So my laptop can do like 44 megs in this test. If we check the demo, then we see that this is synchronous I/O on a single thread. Does it matter if I change the block size here, right? I have an SSD in this laptop. So if I read smaller or larger blocks, will it matter? To put the question differently, is sequential or random I/O behaves differently on SSD? We are so lucky that I have this laptop here, so we can try. If I set the block size to, let's say, 1 meg, it will be a lot faster. So the nature of I/O, if it's sequential or random, still matters on flash storage, but not as much as on spindles. Just the boundaries are at different places. I just changed the block size to 1K, and for 1K blocks, performance will suck. It will be slower and slower if I lower the block size, but if I lower it under 4K, which is the physical block size of the device, here I'm not writing I never write 1K, I always write 4K at the physical level. So this is why if the block size reaches a certain size, then it will get a lot more slow. So this is a graph of the write throughput of my laptop in case of asynchronous I/O, and we decided this says that the number of threads doesn't matter, and this is a graph on the response time in milliseconds. And let's stop a bit here. Is this graph good? Why not? Because otherwise I wouldn't ask, right? So what is not visible from this graph, right, that the response time is around between 10 and 20 milliseconds. But is it more like 10? Is it more like 20? What's the distribution, right? That's why I like jitter plots, because from this plot we will see that 10 is more frequent because we have more frequent samples. And we can see that it's more like an either-or relationship, that sometimes it's 20, but more or less it's 10. And the other good answer for is that graph valid is that can we measure the response time accurately in case of asynchronous I/O? And we can't, because we don't wait for the completion of the actual I/O. We will check back later if the I/O operation is completed, and we can record the time when we get the results from that check. But at that time, the I/O operation may be completed for a while. Okay, So this is again the write throughput, and here it is visible that the read throughput of my SSD is much higher. So it can read much faster than it can write. And we can also see that the read performance is consistent. From the jitter plots, I like to use alpha channel for the individual dots. So if they plot it on top of each other, it will show a sharper color. And here you can see the read response time. Sysbench can also do mixed throughput, and this is one rookie error that usually people make, that okay, my storage can do 400 megs of reads, so it will be okay. But as soon as you mix them, the read performance, the characteristics of read performance will change. So if I do reads and writes at the same time, I'm not able to do 400 meg read throughput anymore. So it seems, and here is the response time of this graph, and the red one is the read throughput, and the blue one is the write. Okay, so in last November I started a MySQL instance, and it wrote that it is using Linux native asynchronous I/O. And I told you at the beginning that we will discuss results for synchronous I/O. So do we have to do it at all, or we can stop here? Because it doesn't matter. It does matter. Asynchronous I/O is used for checkpointing, but for example, the redo loads are written synchronously. And this is the synchronous write throughput. And this graph doesn't have time in the x-axis, but rather the factor of the number of threads. And if you check this one, so the write throughput at a single thread, why is this important? In MySQL 5.5 and in 5.6 if you have a single schema. Because replication is single-threaded, right? Which means that that replication can't go faster than this. Why? The throughput of my storage at 16 megs is a lot better. 16 threads is a lot better. CPU?
CPU, the cores? The number of cores?
2. So but the benchmark is not CPU intensive.
No, I mean thread.
Yes, so I use this many threads, but this laptop has 2 CPU cores.
Yes.
Okay. So if you graph the response time, you can see that up to a point, up to 16 threads, the response time somewhat increases. But after a while, if I keep adding threads, the throughput doesn't change too much, but the response time will skyrocket, right? So, and this is another point to make, that every system has an optimal degree of parallelism, and if you go over that, then you will get horrible response times. And this is why it is a bad idea to set max connections for MySQL to 10, 20,000 or something like that, because if you start using all of them, this will happen. Similarly for reads, so if I use more threads, read throughput will increase. But again, similarly, the response time will just blow up after a while. And this is for mixed. So similarly, my read performance in isolation was pretty good. But if I do a mixed benchmark, I won't be able to do 400 megs for reads anymore. And the response time is pretty similar. So after a while, the throughput doesn't grow, but the response time starts to grow exponentially. Okay, so far this was fileio, benchmarking your IO subsystem. And now let's talk about benchmarking MySQL. Here is how you can prepare a test database. So you create a schema and use that schema and use the parallel prepare.lua script to create your test database in parallel. And here is how do you do one benchmark iteration. One more thing with this is usually you write scripts like this, that for all test modes, for all IO modes, for all thread configurations, you do the benchmark, and at the end you will aggregate it. Similarly for, this is how a typical OLTP benchmark looks like, that you vary the number of threads and you measure each thread. If you want to vary another parameter, then you can do it as well. So I recommend to write basic wrapper scripts like this. I think the most well-known benchmark in sysbench is OLTP. It has some parameters like the table size, and it has some parameters for its queries as well, like what should the range size be, how many point selects should be in a transaction, how many simple ranges should be in a transaction. This is, by the way, in sysbench in command.lua, so you can find the definition in command.lua. And for database benchmark, I chose to examine a workload now which reconnects pretty frequently. So we won't do the OLTP benchmark now, but I would like to show you how can you use sysbench to reproduce an issue which you may see in the production environment in kind of a sandbox by modifying the Lua. So let's edit. Let's examine too much sysbench. Let's examine the update index.lua, which we will use for this. And I modified this script a bit, that in the event function, I do a DB disconnect, which means that after every transaction, sysbench will disconnect from the database. So what do I simulate here? Let's say a PHP application, where the PHP interpreter only runs while the HTTP request is alive, and every time it will reconnect to MySQL. So, if I do the benchmark without the reconnect, then it will be okay. So, this is the throughput we get for updating by single primary key on 32 threads. Here the tables used in the benchmarks benchmark is rather small, so all of this is in memory. But if I add the disconnect back, and do it again, then for a while it will be kind of okay. You can also see that in MySQL the connections are cheap, so it doesn't matter that much if you are reconnecting or not. It matters a little. And now MySQL sucks, right? Oh, it sucks again and again. What happened? MySQL is not running? Yes, it is running. Oops. It sucks again, still. What happened here? No? Also gets in time wait. Yes. So the issue here is that when you close a MySQL connection, the protocol level, the MySQL protocol level close doesn't close the TCP/IP level connection. So if I check, all sockets will be in time wait, and here I'm actually out of the local IP and port range for TCP/IP. How can I fix that? I can limit the number of connections at the kernel level that can be in time wait. If I limit this, then I can't have more than 1,000 connections in time wait. The kernel will simply kill it, and my benchmark is fixed now. Okay, and this will run like forever because I won't go out of the local of the port range anymore. So if we do this again. We keep at roughly 1,000 because the rest is killed by the kernel. If we check what happens here, no, it's not here, but here if your traffic is high enough, then the kernel can complain that it killed TCP/IP connections. I tried to break MySQL connections with that and I wasn't successful. So looks like these TCP/IP connections are there for like no reason. When you close the MySQL level connection, the server doesn't initiate the TCP/IP level connection, but it is initiated by the client later, so the connection will be reused. I don't know if it would be better for the server to initiate the TCP/IP connection close when the client thread is closed. Okay. So, thank you everyone. One more thing, which I almost forgot. My colleagues and friends from Belgium are organizing a community dinner, and they asked me to show these slides. I haven't seen them myself, so I will check it out with you and improvise. This is the first one. There will be 3. It has some nice logos on it. I guess that they are the companies who are sponsors, right? Yes, okay. In this slide there are some text and the map, and the text says which bus should you take to get to the community dinner. So this is kind of a useful information part. And here is bus and table. So you don't have to stand in the rain.
You can have the previous slide.